Hello my dear students, I hope you are enjoying this series on vector calculus. Vector calculus plays an important role when we are dealing with the problems of mechanics or fluid mechanics, right? Because velocity, displacement, all are vectors. So in this video we are going to talk about a very important concept which is unit tangent vector. So let us make a picture of what we have right now. We have a curve, right? So you have a curve. Okay, so you know how to define a curve. To define a curve, we have a parameter t. Generally, this is time. And then from this parameter, we define a vector xt, which can be of any dimension. For example, if we are in 3D, this can be x1, x2, x3. Okay, so you have a parameter t, and then this function, we assume that this is a C1 function. So there are no corners. And most of the times since a particle moves along this curve, so we assume that x dash t, which is velocity of the particle, because if the position vector of the particle is x of t, then the velocity of the particle is x prime t. So we assume that x prime t is non-zero. Okay, so these are the things we assume, right? So this is a curve, and then in the last video we said that, okay, what if we fix a point, say p naught, right? And then for any point p, this was the distance s, right? And we wanted to parameterize in terms of s, not in terms of t. So this s is an internal candidate, right? So we want to parameterize in terms of s. Then we saw that s of t was 0 to t, the modulus of the velocity vector, okay, tau d tau. This is what we saw, and we saw that from here we can find out, we can write t in terms of s and then replace our parameter. So this was the story. So this is the summary of what we have done in the last videos. Okay, so this was a recap. Now, in this video, we are going to define the unit tangent vector. So suppose this is my curve. You can take any curve, okay? We can take a simple curve also like this. Okay, so this is my curve. I want to look at the unit tangent vector, right? Unit tangent vector. So everybody knows what is a tangent vector. So the position vector here is xt. So at a point, the tangent vector is going to be x prime t, and the unit tangent vector is going to be x prime t divided by its magnitude, x prime t. So we define the unit tangent vector is x prime t divided by x prime t modulus. So this is tt because it also depends on t, right? So at every point we have a unit tangent vector. Does that make sense? Now we would also try to find out what will be the unit tangent vector in terms of the parameter s. Okay, so let us look at that. So we just saw that s of t was 0 to t x prime tau d tau. Now here, if you differentiate it with respect to t, can you see what you are going to get? If we differentiate it with respect to t, we will be getting, so you can use the fundamental theorem here. So this is equal to x prime t. Okay, so this is your ds by dt. Now, what is x prime t? That is dxt, derivative with respect to time. I can use chain rule and I can introduce the parameter s in between. So this is the chain rule We all are familiar with the chain rule. Now, what is this and what is this? Right? This we just calculated that this quantity is equal to x prime t, and this quantity is nothing but, this will be s now, right? So what we are doing here is we are changing t in terms of s. So this is x of s, right? Do you understand? So this is x dash s. So we get x dash s into x prime t is equal to x dash t. So from here you get x dash s is equal to x, this will go in the denominator. So you'll get x prime t divided by modulus of x prime t, which is nothing but the unit vector. Okay, so hence we now know how to find the unit tangent vector. So we have two ways. One is simply I find, if I have my parameter t, so I can find the derivative and its modulus. We divide them, I'll get the unit tangent vector. Or what I can do is, if I have it in terms of, parameter s, then if I find x prime s, that is also unit tangent vector. Does that make sense? Okay, so let us look at an example. We'll take a simple example. And in all this, we are dividing with x prime t modulus. So this makes sense because we are assuming that the particle has, never a zero velocity when it is moving along the curve. So now look at this problem here. For the helix xt equal to a cos t, comma a sin t, comma bt, right? Now suppose this is my helix. I want to find out and p naught is a point because I want to do it both with the parameter t and s. So p is a point which is corresponding to t equal to 0. Okay, so p naught is that point and s is the parameter which denotes the distance of a point from p naught, which denotes the distance of a point from p naught. Okay, so now let us see. I want to find out the velocity unit tangent vector here. So one way is I can go for x prime t's modulus and then x prime t. So that is going to be, if I differentiate it, I am going to get minus a sin t I cap plus a cos t j cap plus b k cap. So I just differentiated these components, and then the modulus will be this square minus a sin t square plus a cos t square plus b square. So that would be minus a sin t I cap plus a cos t j cap plus bk upon square root of a square plus b square. So this is the unit tangent vector. This is the unit tangent vector for this particular circle, right? Now let us do it in terms of s. So we know that, first of all, I told you that you have to calculate st, which we already did in some previous video, but we'll do it again here, no problem. So this was x prime tau modulus d tau. We just calculated the modulus here. So this is a square plus b square d tau 0 to t. So we get s is equal to square root of a square plus b square t. So we get that t equal to s upon a square plus b square. So what is my x of s? I have to replace t with s. So I get a cos of, in terms of t, it is s upon square root of a square plus b square, comma a sine of s upon square root of a square plus b square, and then comma b s upon s a square plus b square, right? Now I know that unit tangent vector equal to simply the derivative of this. So that is going to be differentiated with respect to s. You will get minus a sine of s upon a square plus b square I cap times the chain rule, the derivative of this, which is 1 upon a square plus b square. Similarly, for the second term, it would be a cos of s upon a square plus b square into the derivative a square plus b square j cap, and then the derivative here, which will be s upon a square plus b square k cap. Right? Now, if you use the back definition, so what you'll be getting, this is nothing but t. This is t. So we want to match this vector here. This should be same as this vector, right? So this is t. So this is minus a sine t I cap upon square root of a square plus b square plus what is this? This is a cos of t j cap upon square root of a square plus b square. And what is this? This you can write as s is t times, right? So s will be your, just a minute, we made a mistake here. This was, if you differentiate with respect to s, we'll get a b. So this is a mistake here, so you should get a b here. So this is bk upon square root of a square plus b square. So now you can match these two vectors, they are equal, right? So in this video, what was the aim? We are saying that now for any curve we have two parameters t and s. S is an internal parameter, and then if I want to find out my unit tangent vector, so one way is I do it like this, and the other way is I do it like this. Okay. Thank you for watching this video. Please share this video and subscribe to this channel. Happy learning. Bye.